active feedback to the system, and that allow me to change the frequencies. Either displacement feedback or acceleration feedback are good. But again, I can't dissipate my energy. If originally my system is oscillating, is vibrating, then I cannot reduce the vibrational energies for this. Okay, that's the acceleration feedback. I'm going to talk one by one and then let you feel it. All right. If I have the velocity feedback, I have the sensor, the measure y equal to w dot, and I say, okay, now giving u, now my feedback u is equal to minus theta w dot. What do I get? My cross-field system is become this. Then my response, my transition response become like this. And now our frequency has been changed by zeta here. If zeta is small, it don't change much. But important sense is we have an exponential function here, e minus zeta t divided by 2n. That means what? That means if zeta is larger than 0, when t increasing, then this term will be reducing. So my response will be decaying. That equivalent to that. I add a despot to it. So that means to a passive system that add a despot to the system. And we know that if you have a despot there, your energy is dissipated. Right? So if you in the Type A 101, you have the direct feedback of W dot, then your frequency will be changing a little bit. However, you will also dissipate the energy coming from the earthquake. If earthquake is shaking and earthquake gone, and that's become transient response, and that is the response you're going to get. And then you're going to energy will go to decay. Now, so the conclusion here is the direct feedback, the only velocity direct feedback will add the despot, equivalent to despot, to a system. That means you will dissipate the energy. The second. So now we discussed three kind of different measurements, and these three different measurements are commonly used in the feedback control design, either displacement sensors, or velocity sensors, or acceleration sensors. Those three types of sensors. That's it. And the cheapest sensor you can use is the XL sensor, the acceleration sensor, because that's, you can buy maybe less than 100 NT, you get one. The XL. It's very, matter of fact, your cell phone, most of your cell phone now has an XL acceleration device there to detect your gravity force, so that when you turn it, your page will turn. That's the all in your cellular phone. Okay. So energy dissipations. the total energy, any system, the total energy will be half m w dot square plus kW, and this is kinetic energy, and this is potential energy. The energy decay, if we have T means the T is total energy divided by time small t equal to m w dot plus k w dot. Then if we take w dot out, if m w dot plus kw, and that equal to minus zeta w dot square. And if zeta is positive, then T dot is negative. That means the energy is decaying. So this is just prove it to you that unless you have the direct feedback, unless you have the velocity device, otherwise there's no energy decay. The only device provides you the energy decay is the velocity sensor. So if you use PID, maybe some of you learn about PID. PID, the D means derivative. So assume you have only displacement, what can you do? If I want energy decay, what can you do? Tell me, if I have only the displacement measurement, but I want to have energy decay. If I get direct feedback, then I cannot get energy decay. What can I do? Is there any way I can do it? Because we know that we cannot, there's no decay if we have a velocity. But unfortunately, your teacher provides you only the displacement device. You may go back to your teacher and say, I'm sorry, I cannot do it. Buy me a velocity field and sensors so I can have energy decay. But your teacher said, no. That's all you get. What can you do? Any way you can do it? Huh? All right. Here. We know that displacement and accelerations, this is only there's no energy dissipations. Right? W dot, then feedback. This is uncalled feedback, direct feedback. W dot will give you the energy dissipation. All right. Now, if I have a device, only W, the displacement device. What can I do to do it so that I can have dissipations? W, there's no energy dissipation. But I have only W. I give you only W. What can you do? Okay, I think I can do this, right? I can differentiate by computer. To differentiate by computer is not difficult, right? Yeah. Well, if you have a very nice sensors, yes, you can do that. If you don't, you do that, it's dangerous too. If you have noise, if this W, you have some noise, then you not only differentiate this, you also differentiate noise too. Alright, now if W is is cosine omega t, right? And W dot is what? Omega sine omega t, right? Right? Now, if this omega is large, then when you differentiate that, you amplify your signal by omega. Correct? Now, if you have noise here, this is plus noise here, then you also have to do a noise differentiate noise. And if you have a high frequency noise, and that frequency is larger than this one, then you're in danger. That means you not only amplify your signal, you also amplify your noise. Your noise here will be amplified when you differentiate. Then this can be very noisy. This can be very noisy. All right. Okay. Now, if I have XL only, then what can I do so that I can have energy dissipation? So I say integrate. Okay. All right. Now, do I have any